Hello everyone, this is Francesca Vigliani from Cloud Academy. Welcome to episode number 2 of our Mastering Machine Learning webinar series. Today we're going to talk about building and running a machine learning pipeline. I'm very happy to see so many returning attendees. I know that Andrea's sessions have become quite popular in the industry. So thank you for your loyalty, for joining us yet again. And of course, a big welcome to those of you who are joining us for the first time. We hope to see you next time as well. Before introducing our speaker, just a few housekeeping announcements. As usual, this webinar is being recorded and will be shared with you via email as soon as it is available. At the end of the session, we will hold a Q&A moment, so feel free to submit your questions through the chat box. I will share the GitHub repo in there, so you should be able to see where the chat is. And in regards to the GitHub repo, let's see who has done their homework or not. Have you set up your environment? If not, please go to the GitHub repository you have in the registration email and be sure you clone it on your local environment. And if you already did that, please pull up the latest version. Don't worry, I will share it in the chat in a second. And just a reminder that this GitHub repo is the same one that we'll be using to upload the scripts of each webinar. Alrighty, I'm all done with the usual announcements, so we can get things going. Let me introduce you to our data scientist, Andrea Giussani.
Thank you, Francesca, and welcome everybody. Nice to see so many people even today. So again, thank you for participating. For us, it's very important that you come here to learn and to participate with me during this hands-on webinar series. So just a brief introduction of myself for those who don't know me. I'm a data scientist here at Cloud Academy where I mainly focus on the development of machine learning algorithm to provide state-of-the-art solutions to improve the quality of our product. You can reach me out on LinkedIn, or you can visit my website for updates on machine learning or Python in general. Please note that this is an hands-on webinar, so I will perform all the necessary steps live with you. However, don't get too much stressed with the code, because you can get the webinar code by the end of this session, and you can basically follow the steps live with me, try to understand the logic, and then off of this webinar you can review the code by yourself, thanks to the fact that I will upload the transcript, the full transcript, on the GitHub repo. Please note also that I will upload the full recording of this live session as soon as we finish the webinar. And again, the YouTube URL will be uploaded on the GitHub repo. So the agenda goes as follows. We are going to understand the webinar topics and the learning objectives, and then we jump into the data and environment we are going to use during this session. And then, as usual, we will use the Google Colab environment to perform all the necessary steps in this live session. So let me say like this. So this is the second episode of our Mastering Machine Learning series. The first episode was dealing with the problem of inputting missing values during the dataset creation phase, which is a very important block when we are speaking about a machine learning pipeline. Typically, a machine learning pipeline is divided, let me say, in 3 steps. You have a phase where you basically wrangle and manage your data in order to create a dataset that is going to be the input source for your model. And here comes the second major block, which is actually the training phase, where you pick a model and you ingest that model using the data that you produce during the dataset creation phase. You train a model, you get some results, and then that model can be used to perform some inference on new data, which is typically called prediction. So today we are basically focused on the whole training and test pipeline by looking at a particular application, namely a natural language processing pipeline. And in particular, we will use the Python as the backend language. And in particular, we will focus on standard NLP, and we will make use of the scikit-learn library to do that. Why scikit-learn? Well, for two main reasons. The first one is that we actually started understanding the library in the previous episode, and therefore we got an understanding of how scikit-learn works during in a machine learning pipeline. And secondly, we are going to use scikit-learn because it actually includes several methods that allows you to perform simple standard natural language processing techniques, such as the bag of words or the term frequency inverse domain frequency techniques that we are going to use today. And last but not least, I strongly suggest you to follow this webinar if you are basically interested in learning how to perform machine learning with Python, thanks to our 5-episode series. This is not a strong requirement, but I suggest you to have an intermediate Python language knowledge in order to successfully attend this webinar. It's not compulsory. You can just watch my step that I'm going to perform live today with you, and then in case you can look at back, as I said before, after the webinar. And last but not least, the software we are going to use during this webinar is 100% free and open source, which means that actually everybody can start learning machine learning with Python without basically any effort from budget and as an hardware point of view. So after this webinar, you will be able to understand how scikit-learn works to perform natural language processing and what an embedding is. This is a crucial concept when we speak about translating text into a machine learning pipeline, and we are gonna get back to this concept in a few minutes. We're gonna understand how to train a classification model. Last time, if you remember, we saw a situation of where we were working with data, and in particular with imputed values. Here, instead, we are going to understand how to train a model with scikit-learn. And last but not least, we are going to perform basically inference on unseen data, thanks to the fact that we have trained a model using scikit-learn. Since this is an NLP-based webinar, I have to say that there exist many NLP techniques in the wild. And this webinar somehow will be strongly based on NLP. And in the next few episodes, we are gonna exploit and understand even modern NLP techniques. So don't worry if you don't know NLP too much, because by the end of this 5-episode series, you will get an understanding of how NLP works, and in particular, the recent developments on this fantastic area. But having said that, today we will focus on a very standard technique, natural language processing technique called Tf-Idf. And the Tf-Idf typically is used to transform basically a text or a list of text into a numerical representation. What does it mean? It means that, so basically, from a theoretical point of view, the term frequency inverse domain frequency, it's a technique that allows you to extract some numbers, a statistic that reflects how important a word is to a document in a corpus. And typically, when you apply a Tf-Idf, you actually convert a document into a row of your Tf-Idf metrics, and we are going to understand today what a Tf-Idf metric is, and each single word is stored in a column vector. And therefore, you can see these Tf-Idf metrics made of rows representing documents and columns that represents each single distinct token or word that appeared in the corpus. So we are going to use that in order to produce an embedding, and we will see how those embeddings are used by a model in order to perform classification. As I said at the beginning, we're going to use the Google Colab to perform the live session. If you have followed my webinars, you should be pretty familiar with that environment. If not, don't worry, because I have written a README on how to set up a Google Colab. And I assume at this stage of this webinar that you have read and set up the environment, since all instructions were provided before the start in the registration email. And as far for the data, what we are going to do is actually we're going to use news, a dataset that contains news from the BBC dataset. And we will try to classify those text using, as I said, NLP techniques and scikit-learn. It's important that you have it. So if you are using some Jupyter notebook locally, please be sure that you have it on your local environment. Otherwise, you can just clone the GitHub repo on your Google Drive, and everything will be there. Okay, so we can actually jump into our session, and as usual, we are actually working with a Colab environment, which actually is pretty useful because we have actually a Python env with an IPython shell available for free. So what we have to do is actually the first thing that we have to do is mounting our drive into the Colab session, and this is actually a standard snippet that we have to do before our development. So by running this simple snippet, we are gonna allow Google to read inside our drive. So we actually allow that. You just copy and paste the code, that the authorization code that Google is providing to you. And once you have entered the code, it takes a few seconds. And after that, you see that your drive has been mounted inside the Colab session. So we are actually ready to look into our drive. You see here a few folders. So what I had to do is actually picking the folder where I stored my data. In my case, I stored this into this folder. I'm gonna copy. And so I'm gonna copy here the data path, which is this one in my case. So yours, I don't know, but it's gonna be pretty simple for you to retrieve it. And if you remember, if we go here, the data are made by these three files. So we have a train set, a test set, and basically this file that contains actually the true labels that are used in the test set. So for the moment, let's forget about that. But the most important thing now is that we are gonna read the file called BBC News Train in order to perform all the necessary steps to fit a model, a classifier. So if you have downloaded the file from the GitHub repo, you should find all those steps that you see here already available in the notebook. Otherwise, you can just follow my steps here. So here I'm gonna import pandas SPD just for simplicity, because pandas is quite a popular library in order that is used to perform data management and wrangling in Python. And I also import OS, which is used basically to perform some operation like joining two strings in order to define a path. And as you remember, the PD read CSV function is used to read a CSV file, as in our case, the BBC News Train CSV file, and is returning that CSV file into an object that is of type pandas data frame. And a pandas data frame, we know that it's actually a useful object that allows us to perform data manipulation and wrangling in an easy way. So once we can inspect the first 5 rows of the training DF, and we see that we have 4 distinct categories, 4 distinct columns. The article ID, which is an identifier of the article from the BBC News tray, the BBC News dataset. The text is actually the clean text, because you see here it's a lowercase text, and it contains basically the text related to our news. And the category is actually the target label. It's a label associated to that particular text, and we can see easily that we have a few categories in our case. So in order to check that, we can actually perform this simple step. We can access to the columns, let me say text and category, and we group by with respect to the category itself in order to count each single category that appears in this dataset. So this simple syntax allows us to produce this table, which says that we have 5 categories, and I would say they are pretty homogeneous in the training set. So business appears 336 times, and so on and so forth. But as I said, they are pretty homogeneous. So which means that the target is spread well inside the training set. And this is a good feature, obviously, of our data, since we know for sure that each single category is well represented inside the training set. Before jumping into the dataset processing, I would like to perform an extra step with you live, and this goes as follows. What I want to create is Python dictionary that with keys has, let me say, a number, and with value the category that we have observed. Why am I doing that? Well, because then I want to encode the category column inside the train data frame by creating a new object, a new column that will contain the actual label translated into a number. Why is that? Because typically any algorithm doesn't work with a categorical variable. So we have to encode the label, the category column, which is by default a categorical variable, into a number. And to do that, I can do the following. So I can define the categories list, which is an object that is created by the train DF, and I take the category column. I also drop the duplicates, and I store this into a list. Okay, so in this way we can get a list of our categories, distinct categories that represents our training set. Then what we can do is creating an index list, which is a list, obviously, that contains an integer associated to each single category. So what does it mean? It means that we can perform a for loop, and this for loop contains elements that are taken from the range in the length of the category list that we just created. And this index list, without no surprise, will be a list of 5 numbers going from 0 to 4. And as I said, my objective is to create a dictionary that contains keys described by these indexes and with values that describe the category itself. So what we can do is actually creating my category mapping, which is basically a dictionary made by, let me say, 2 elements, 2 lists, and we zip those lists in order to create the dictionary. And I zip the index list and the category list in this way. Here is the result. As I said, a simple Python dictionary containing as key the indexes and as values the number of the categories, the number of the distinct categories observed in the training set. So why am I doing that? As I said, we want to basically translate this category column from a string to a numerical representation. And to do that, we can do that in different ways. The most simplest, the simplest one is actually to encode that category using the pandas factorize method. And the pandas factorize method encodes the object as an enumerated type or categorical variable. And it is useful to use this method when we want to obtain a numerical representation of an array when all that matters is identifying distinct values, as in our case. So to do that, we actually can do the following. So we are going to create into the train data frame, we create a new column, and I call this category data frame. And this is nothing more than the category column from the original data frame. And we apply the factorize method. And we take, since the factorize produce a list, we actually take the first element of that list of lists. And if you now try to inspect the first 5 rows, you see that you got a category index associated to each single category in string. So this is pretty useful because we have avoided somehow applying strange or very tedious snippets that produce the encoding of a categorical variable into a numeric variable, let me say. And this categorical mapping will be extremely useful in a few seconds. So we got that. And what we want to do now is, okay, I have this data set made of 4 columns. Those 2 columns are actually the same thing, and we are going to use the category IDs, not df, much better. Otherwise, doesn't make any sense. So we're going to use the category ID. And what we have to do is actually, before feeding a data set into a model, we have to translate that text into a numerical representation. And here comes the concept of embedding. In the previous slides, I explained what an embedding is somehow, and I told you that we can create an embedding in different ways. The simplest way is to use the term frequency inverse domain frequency technique, which is a technique that actually allows you to weight each single word with respect to the importance of that word inside a document. And why is it useful? Because you can actually translate a string which describes a document, in our case a news, into a numerical into a number, a statistic that describes the importance of that word with respect to the document. And the Tf-Idf vectorizer from scikit-learn is actually a class that allows us to generate a Tf-Idf matrix given an input that is made of a column of text. So basically the input is going to be this column of text, and each single row describing a document is going to be converted into a numerical representation where each single column of the Tf-Idf matrix will be each single token, distinct token, in the corpus. So we perform that, and in particular, we use the Tf-Idf vectorizer. If you have attended the first episode, you should remember that we focus in that episode on the class of transformers. Scikit-learn has two major classes, the transformers and the estimators. The Tf-Idf vectorizer is somehow a transformer because it actually ingests some data and it returns a different representation of the original data. And in particular, we use the feature extraction.txt submodule. And since it is a transformer, it is going to be characterized by two methods, a fit, which actually learns some pattern in the data. In our case, the term frequency for each single document, and the transform, which actually return the Tf-Idf matrix representation of the document. So to do that, we actually initialize a Tf-Idf vectorizer, and I store this into the Tf-Idf object. And the Tf-Idf vectorizer has many arguments. So today, unfortunately, we are not able to see each single of them. But I would like to pose the attention on at least 5 crucial arguments. The first one is the stop words. So when dealing with a natural language processing pipeline, you typically want to exclude some terms that are very popular. And why is that? Because actually they bring just noise in the process of the text. But more importantly, those terms don't bring any information, any relevant information on the document. So the stop words that are typically identified with some list for each single language. In our case, we are going to use the English stop words, are going to be removed from our text when the Tf-Idf vectorizer will be applied to those texts in order to clean the input data with in a more consistent way. So this is the stop words. Another very important is the min df argument, which is the minimum number of documents a word must be present in order to be kept. And we set this equal to 5, meaning that we are going to retain only those words that have appeared at least 5 times in our corpus. This is to avoid, this is for many reasons. First of all, to avoid the presence of rare words, which drastically increase the size of our feature in the Tf-Idf matrix. And very importantly, this might cause overfitting. So we don't want our model to overfit on some specific documents. And so we want to remove those documents that contains rare words. And to do that, we have used this simple argument. Then we can use the sublinear df, which is an argument that is a Boolean, can be set as true or false. If set to true, use a logarithmic form for frequency that allows to basically to diminish the returns as frequency as the word increases. So basically, it's quite it's a logarithmic trend. So basically, if you know a little bit of math, you know that the log somehow after a while it has a smoother behavior, and therefore we are going to apply basically the same logic here with the Tf-Idf. Note that this argument is not strictly necessary, but I wanted just to mention here in this webinar. Then a very important one is the norm, and I set this as L2 to ensure that all our feature vector have Euclidean norm of 1. And this is very helpful for visualizing those vectors, and can also improve or deteriorate, obviously, the performance of some models. Last but not least, the Engram range. This is pretty important, and I strongly suggest you to check by yourself this in order to get more. Basically, this is we are going to set as equal to a tuple made of 2 numbers, 1 and 2, to indicate that we want to consider both unigram and bigram. So in other words, we want to consider single words, let me say here, German, business, confidence, and so on and so forth, and pairs of words, German business, business confidence, confidence light, and so on and so forth. Why is that? Because sometimes considering pair of words give us a better understanding of what's going on inside the text. So we initialize this class, and sublinear df, tf, sorry for that. So once we have initialized the class, I said it is a transformer, like our last time. We know that a transformer has 2 main methods, a fit and a transform. And so we're going to apply the fit and transform method to what? To the train df on the text column. And we also want that that result to be an array. And we store this into the capital X, standing for the set of feature, and the Y is nothing more than the train df in the position category ID. So here is fitting the model. So just to give you an idea, the X is an NumPy array that contains, it's a sparse matrix, obviously, in which you have a lot of zeros and some numbers, and those numbers indicates the Tf-Idf score for a particular document with respect to a word that is a column in our case, whereas the Ys is actually the labels we wish to predict for each single document. So once we have done that, we have basically produced a data set, and remember, we started with a text, okay? And now our set of features is not anymore that plain text, but it's a Tf-Idf matrix. And each single list here is called an embedding for the document that is represented by that row. So namely, the one that you see here highlighted, it's the numerical embedding of the first text in the train df that goes as follows. Let me check. One. So yes, it's this way. When indexing, let me do like this. Let me do like this. Here we go. So here is the text. You see it's a lot of stuff. So this text is translated into this numerical representation. Here we go. Where each single number describes the column that you have in your Tf-Idf matrix. So forget now about this text. We are gonna work with the Tf-Idf matrix as input of our model. Why? Because any model works with a numerical representation. It can't work with text, right? With strings. That's why we convert categorical variables into an ID, some numbers, as we did before, and that's why we convert a text into a Tf-Idf matrix. So once we got that, we want to fit a classifier, and I've chosen here two classifiers, the logistic regression and the random forest classifier. The logistic regression is pretty standard in the literature. It's a linear model that is used to perform classification. If instead you want to go beyond linearity and you want actually to use more sophisticated models, the best choice is obviously the random forest. And it's not here the session where we're going to speak about the technicalities of each single model. If you are curious, you can check our content library where you can find a few courses that explain you the mathematical details of the logistic regression and of the random forest classifier. And I also import the cross-val score from the model selection submodule because we want to actually perform some evaluation of those two models. In other words, we want to answer to a simple question: which model is the one that fit the best the data? And to do that, I'm going to create a list of models. The first one is the logistic regression, and I set a random state equal to 0 for reproducibility. This argument is actually used to allow researcher and colleagues to share the results in a reproducible way. So it's always important that you set it. And the random forest classifier, again, has a random state of 0. Obviously, we can set also other arguments because this is a nonlinear estimator. It's an ensemble, so we can use n estimators equal to 200, and the max depth of each single tree in our random forest is going to be 3. Don't worry if you don't get all those concepts. Again, if you want to improve your knowledge, we have a few courses in our content library where you can learn those kind of concepts. Okay, so I set up this list of models. And be careful, we are moving away from the concept of transformer. I want to stress this fact again. A Tf-Idf factorizer is a transformer characterized by two methods, a fit and a transform. Now we are moving away from that word. We are speaking about models, estimators, and the logistic regression and the random forest classifier are indeed estimators, which are characterized by two methods, a fit and a predict. A fit typically learns some pattern in the data, and a predict actually use that knowledge to predict on unseen data some labels, okay? And in order to find the best model, I have produced for you this snippet, this method that I call the getting models matrix, that for each single model is gonna fit a cross validation, and it's gonna return for each single fitted model its best score. So let's try to use this. And so here is missing the semicolon. Sorry for that. Also, there was a mistake here. He has to return the Tf-Idf and not the full line. So just return the CV here. And what we can do is actually calling these methods. This method requires two arguments. The CV param, which we set this as equal to 5. You can set as equal to 10 in case you want to see more fit, but for simplicity here, I'm gonna set this as equal to 5 in order to speed up also the process. And then the models, which is nothing more than the list of models that I created here. So we run this simple method. It takes a few seconds, obviously, because we are fitting 10 different. Each single model, we have 5 cross validations. So we had 10, and then we had 10 models, okay? It takes time, obviously. But once we will get this, we will get a pandas data frame containing the model name, the index of the fold, and the accuracy. And based on the accuracy, we are gonna choose our model. So pay attention, here you have 5-fold for the logistic and 5-fold for the random forest. It looks like that the random forest is not performing better than the logistic. So we focus on the logistic, and you see that the logistic somehow has a better accuracy than the random forest. And also to be sure that we are looking at to the correct stats, we can group by with respect to the model name, and we can take the average of the accuracy. So basically, the logistic regression on average performs 0.97 of accuracy, whereas the random forest is 0.85, which is good. Both models are good, but if we had to choose, we are going for the logistic regression for two reasons. First, because it has a higher accuracy. Secondly, because it's a simpler model. And so if you can go with a simple model, why not? Let's do it, okay? So we are going to use the best model. And so I'm going to use the logistic regression with a random state equal to 0. And then I fit that model on our set of features, the Tf-Idf matrix, and the set of labels. Okay? So we fit the model on our logistic regression. And we get this model with some hyperparameters. If you are curious, you can check by yourself, but that's not important at the moment. Obviously, it's important if you want to perform hyperparameter tuning, but for the moment, it's not so important, so crucial, because what I want to actually expose you in this webinar is the process, is the full pipeline in scikit-learn. So once you have fitted an estimator, in our case, a logistic regression model, it's an estimator, so it is characterized by two methods, a fit and a predict. A fit learns some pattern in the data that are being used by the predict method to predict on unseen data. So the question is, how does it work? Well, I have here a test file name called BBC News Test, and we are going to read it, and I store this into the object test-df. And if you pay attention, and let's inspect the first 5 rows, we don't have any label. So we are assuming that once we got some model after a training, we want to see how our model performs on unseen data, so the so-called inference phase. And that's pretty important, because when you go in production with your model, you know, you don't know what will happen in the future. So this is quite a simulation of what will happen in the future, because you don't know the label, but you just get the input, the text of your news, and you want to classify that text with respect to the 5 categories that we have observed in the training. And so how can we do that? Well, it's pretty simple. We have basically to transform the data as we did in the training phase, and then we apply that transformed data to the model in order to obtain some new prediction on those data. So let me say like this. So we are going to actually create a next test, which is a set of features, and to obtain those set of features, which is the numerical representation, the embeddings of our text, we use the Tf-Idf model that we have used in the fit, and we transform the text column, right? So we get the text, the test set, and then we are going to basically predict using the model and using in particular the predict method on the text test. So the first line basically convert the column, the X test text column, into an embedding, okay, or better, embedding a Tf-Idf matrix. And then here instead we get actually we predict the labels based on the Tf-Idf matrix. It's pretty simple, right? And this is pretty crucial in any machine learning pipeline, because once you have fitted a model, in prediction, the data must be processed in the same way as in the fit. Otherwise, the model is not able to learn those patterns that, or better, is not able to apply the learned pattern to unseen data. And to do that, you basically perform these 2 simple steps. Okay, so once you have done that, what we can do is the following. So we can actually inspect the prediction, which is a numeric array as expected. But we, as human, we want to convert those numbers into a category, into a string. So to do that, I'm going to perform this simple step with you. So I'm going to concatenate using the concat method, the pandas concat method, Tf-Idf, with a new data frame that contain the ypred that we just computed, and by using the columns that are the ypred, okay? And we do that with axis equal to 1, since we want to append each single column in our data frame. And then we are going actually to, do you remember at the beginning of our session, I was creating this mycat mapping, and now it's gonna come pretty handy, because remember, now we have predicted some numbers, but now we want to go back to the meaning of that number. How can I do that? Well, I have a dictionary that maps each single number with a category. And to do that, we just need to apply. We can create a new column, ypred label, let me say, which is nothing more than the test data frame enriched in position ypred, which is a number, and we apply the map method to the mycat mapping. So look at this. This is pretty magic. The magic goes as follows. Now we have a data frame with the ypred, with these numbers, and the label associated to that particular number. So now we have to answer to a simple question. I got some prediction. It looks pretty cool because, for instance, here they are speaking about injury, Middlesbrough. I understand that it's speaking about football and therefore is sport. Here is speaking about software and therefore is a tech stuff. Queen's Park Rangers, it's a football squad, so it speaks about sport. And so somehow, by looking at the text, I can understand that as a human that the model is performing well. But how well is performing? That's the main question. And to do so, to answer to this question, I'm going to use this file, the BBC News sample solution that contains the true label. So I'm going to run this simple cell here. And then what we can do is the following. We are going to create a new object, full Tf-Idf, which is the Tf-Idf enriched, and we merge with the y-true on the article ID. Again, if you don't get each single pandas method that I'm applying, don't worry. Either you can go on Cloud Academy, you can learn those topics in our platform, or you can watch our webinar series on pandas that we had in the previous 6 months of 2021, or you can check the documentation in case you are familiar with it. So we merge on the article ID the two data sets. And just to give you an idea, this is the first 5 items. So you get the prediction label and the true label. And what we can do now is, again, mapping back the true label to the category ID. And therefore, I can basically apply again the method that we used before, the factorize. So I'm gonna copy and paste here for simplicity, and I'm going to change the names, obviously. So here, test full Df category ID, and I call this y-true for simplicity. Full test Df, and we pick the y-true label, and we factorize it. Here we go. So you get some, oh, well, it's, yes, I made a mistake because here is not is not able to recall the fact that sport was mapped into 3, so he's right. So let me do like this. So I'm gonna call category ID df, and I'm going to take the train df. It's a little bit tedious, but it's fine. The category and the category D. So we had to overcome to that problem, and to overcome to that problem, I'm going to take each single distinct item and I sort by category ID. So in this way, we are getting a data frame that contains each distinct category with the associated value from the train. Okay, so that we know that sport is associated to 3 and business to 0, because here they flipped somehow the values, and we don't want that. Otherwise, we get crazy. We don't know what's going on. Here we go. So business is 0. I say again, sport is 3. Perfect. So we got that, and I can say category 2 ID is actually a dict containing the category IDDF, and I take all the values. So I created here a dictionary. You see, business is associated 0, entertainment 4, and so on and so forth. And if you remember, my cat mapping, it's different. It's the other way around. For each single value, we have associated a label. So now we have to go on the other way around. So category 2 ID, we just created with this simple syntax. And then by the end of the day, what I had to do is taking the full test df, I create a white true column. And this column is nothing more than the full test df in position white true label. And then I map what? This category to ID. And now it should work. Here we go. Pretty happy now. So sorry for that, but I forgot that we needed the consistency with the training and the prediction. And to do that, I overcome to that problem with this simple three lines of codes. So once we get that, the question is, how can I evaluate the performance of the model? In the last 2 minutes of our session, I can use the metrics from scikit-learn. So we have at least 2 ways: the multi-label confusion matrix and the classification report. So the multi-label confusion matrix is going to compute a confusion matrix for each single label, and the classification report instead is going to report you the precision, recall, and F1 score, F1 score for each single label predicted on the test set. Again, if you are not familiar with the difference between multi-label and the standard classification problems, multi-label problems are typically described with 3 or more categories. Classical classification is based on 2 categories. So here we have 5 categories, and therefore we are in a multi-label case. So what we can do is actually first, let's compute the classification report, which is going to be the full text df dot white true, the white true and the white pred. Yes, he's right. We have to import it. So here is what I'm saying. So this is actually a report, and it's saying these are the classes that for the class 0, which is the business, we have a precision of 20 with a recall of 24. And the support is 147 elements that belongs to that particular class. And so if you pay attention, the precision is not so high as we expected, and even the recall is not so high. So this means that the model is not performing pretty well, which can on the test set, which means that either we have to go back to the train and perform hyperparameter tuning, or possibly the model is the prediction test set, the test set is made of text that were not observed in the training phase. So either those are the two situations. And then the multi-label classification confusion matrix instead use the same data, the white true and the white pred observed in the test set, and returns for each single class the confusion matrix. Namely, these are the true positive, these are the true negatives, these are the false negative, these are the false negative, and these are the false positive. And so for each single class, for each single label, 0, 1, 2, 3, and 4, you got 5 different tables that describe basically the number of true positive and false positive for each single class. So that's pretty much it from my side. I see a few questions. So which type of storage and connectivity type would suit best to host the training data? So that's a pretty good question. If you're using a cloud technology, and if in particular if you're using AWS, at the moment SageMaker, it allows you to take care of everything, and in particular, typically when you use an engine from a SageMaker, you store the data into a S3 bucket, because for many reasons, obviously. And therefore, in order to answer to your question, storage, I would go for a S3 bucket and connectivity with a SageMaker if you're using AWS, obviously, in the cloud. Otherwise, if you are performing, if you want to deploy your application, possibly you can set up a Docker container that is gonna take the data again from your S3 bucket, for instance. Can you please repeat the 3 phases of ML pipeline development? Yes, sure. So in my opinion, typically a machine learning pipeline has 3 major blocks: a dataset creation, where you actually perform all the cleaning and all the transformation that is needed before ingesting the data into a model, as we did today. Today we had some text, we converted into a Tf-Idf matrix, and that matrix is indeed used by the model to train and to learn some patterns. The second phase is indeed the training phase, where you learn some data, some pattern in the data, and those patterns are used in the third phase, called typically inference phase, where you actually have new data, new unseen data, as in our test set, and so you don't have the label. And the model is used jointly with those new data that have been processed in the same way as the training to perform prediction. So those are typically the 3 phases. So I don't see any question, any other questions. So thank you for your attention.
Awesome. Yes, indeed, those were all the questions that we received. So that's it for today. Thank you to Andrea for leading the first 2 episodes of the Mastering Machine Learning series. And of course, thank you to our audience. We hope you enjoyed this session. Before we part ways, just a couple of reminders that you will receive the recording of this session as soon as it is available. Please fill out the end of webinar survey that will pop up when you disconnect from the webinar. Your feedback is extremely helpful in understanding what you liked about this webinar, what you'd like to see in the future, what we can improve. So we read everything, all sorts of feedback is more than welcome. If you missed the past webinars, you will find the link to the previous session in the follow-up email, but I also invite you to visit our website, specifically cloudacademy.com/webinars, where you can find all of the sessions that Andrea has done in the past, but also we have other webinars touching on other topics, whether it's AWS, Kubernetes, Google Cloud, and so on. So do have a look, see if there's anything that you're interested in. We have numerous webinars that are available on demand. And of course, if you want to sign up for the whole series of the Mastering Machine Learning, you find the sign up links on our webinar page, also in the follow-up email to make your life easier. And in any case, the third episode will be on November 4th, so mark your calendars. And again, thank you for joining us, and until next time. Goodbye, everybody.